Okay, so then we have these transitions into topological from trivial or from trivial to topological. So, okay, so there are all the numbers. I'm not going to talk about this other topological number for this case, but let's go to another example of system which is actually also relevant. Which is the so-called Kitaev model, Kitaev chain model. So there are many Kitaev models, so this is the Kitaev chain model. Okay. So then we have a look at this Kitaev chain model. So it's a model, it's somehow similar to the to this SSH model. So you will have also some localized state at the end of the chain. The difference is that in the SSH model, what you get at the end is actually are electronic excitations. In the case of this Kitaev chain model, so you have are Majorana states. Okay. So then we'll go through this Kitaev chain model, in which we will need another topological invariant, so a C2 invariant. So in the SSH model, I show you how to calculate the Whiting number. Now I'll show you another topological invariant that you can use. Actually, for this Kitaev chain model, actually for the Kitaev chain model, you can also use some trick and then describe it with a Whiting number, but just not to repeat myself. So let's try something different with it. Okay. And then if there are some time, so I can talk a little bit about all these ideas of topological quantum computing with Majorana states. So what is the Kitaev model? So this is a model introduced by Kitaev quite a few years ago, and it's essentially a model for a p-way superconducting chain, and it's given by this Hamiltonian here. So you have, so again, the Fermi energy. In the Hamiltonian, you have the first term with this chemical potential, and the C operators just are creation and annihilation operator at a given site. So it's a type banding like Hamiltonian, okay? And you have n sites in this chain, and then we have the hoppings, and then we have this delta, which is in that case the superconducting gap, okay? Yes?
The chain means it's a 1D situation.
Sorry? The chain, yes, is a 1D, yes. It's 1D. All right, so we have this delta. We will see now, after that, what is the specific form of this pairing later on. But this is the model Hamiltonian, and it's supposed to model a little bit the so-called p-way superconductor. So what is the, how to proceed here? The same thing we did with the, to look at the topology. So the same thing we did with the SSH model. So the idea is, okay, we have my finite chain. I will make it periodic, and I will go to K space doing Fourier transform. Okay? So it's the same. So I have my Hamiltonian. I impose these periodic boundary conditions, use my Fourier transform, and you can show that you can rewrite this Hamiltonian in this form. So on this, this look like the matrix elements of this HK, which is essentially the equivalent of this Hamiltonian in K space. Okay. That you will get just from here. You do these calculations in there, substituting in there, and so on. Work a little bit, so this is what you get. This is Hamiltonian. It's a two Hamiltonian. So one thing that I didn't mention is that there is a spin. This is spinless, so there is no spin in there. And of course, you will have a spin. So what he did is assume that the spins are split. So let's say you have a magnetic field, or for whatever reason, the spins are split. And let's say that the Fermi energy is between these split levels, so that at the Fermi energy, I only have one species of this spin. Let's say spin up only at this Fermi energy. Then I can forget about the other. So that's what is essentially done here. Okay. So what will be the symmetry classification of this P wave this key-type model. Will it have time reversal symmetry? Physically, it won't have, because I'm telling you that this spin is split, okay? So you don't see it in, if you can actually, if you treat this like a problem with no spin, because there is no spin in there, and you use the time reversal just conjugation, it will have this, but it's a fake time reversal. It's not a real time reversal, because the real one, you have the other spin, which is not in the, so you get that it have this symmetry because you are not putting the other one. If you put the other spin that you have, then this one, the Hamiltonian won't commute anymore with the time reversal. So it's a fake choice. You can impose time reversal symmetry like the time reversal you will have for a problem without a spin, but it's a fake symmetry. In the system, in reality, you have a spin. It's that you are not considering, okay, this spin in this analysis. Okay, so it won't have time reversal symmetry. What else? Particle Hall symmetry, will it have? It will have particle Hall symmetry. It's like, this is essentially like mean field approximation for a superconductor. It will have this. And you see, this is actually like, it's actually like this BDE Hamiltonian that we have, with some energy minus the energy, and then the deltas in the, right? So it's have this structure that we have before. So it have time reversal. It doesn't have time reversal symmetry, but it have particle Hall symmetry. So since it doesn't have time reversal, so it also doesn't have here, but they have particle Hall, so it doesn't have chiral symmetry. So it only have particle Hall symmetry. So you go to the table, you will see is the D class, only time reversal symmetry, and only particle Hall symmetry, and the particle Hall symmetry in that case is given by this charge conjugation for this specific form of the Hamiltonian, have this form, tau x, this Pauli matrix in particle Hall space, and the complex conjugation. So it is squared to 1. So you go to the table, D class. It's a 1D system, you go to the table, it is described by the C2 topological invariant. Okay. So what is this C2 topological invariant? So we see that it is actually related to a Pfaffian and I will explain a little bit on this. But before starting, so one thing that is important is that so since this Hamiltonian doesn't have this chiral symmetry, I cannot put it in principle in this anti-diagonal form that I could put the other one, because the other one have this symmetry, okay? So I can put the Hamiltonian in the anti-diagonal form only if it had chiral symmetry. But this doesn't have it, so I cannot, in principle, not put it. Mathematically I can, because mathematically it has this time reversal symmetry for spinless particles. Okay? So I can actually, for this problem, I can either consider that this is in class D, just assuming that physically it really doesn't have this symmetry. But if I just want to see the mathematics of what happened to this, I can also use the BD1 class, in which I will have also time reversal and also chiral symmetry. And then I can actually describe it also with a winding number, okay? Yes.
The result will be the same.
The result will be the same because these numbers actually are connected. So I will call it QC2. This is the topological invariant for the C2 for this D class. And it's related in that way. And this is the winding number. So in that case, they are related from the B to from the D class to this is for D class, this BD1, so they are related. And then, so either you calculate nu or you calculate QC. So you have nu, you will have QC. If you have QC, you may not have mu, okay? But if you have the one-day number, in that case, you can also calculate. You cannot do this always, just in this case that you know. You can play with the operators and figure out that there is a time reversal that you can fake it and make it possible to calculate mu, okay? All right, so, you know, in this situation, for this model I can, but typically, if you don't have the chiral symmetry, so you cannot write it in this antidiagonal form, so it's, you know, typically you cannot calculate these winding numbers, okay? So the particle-Hall symmetry, however, also makes something interesting, and it made possible to find a matrix that preserves the determinant of the Hamiltonian, or the original Hamiltonian, and is antisymmetric, okay? So antisymmetric means that fulfill this condition. So you can prove that if there is particle-Hall symmetry, then there is such a matrix that will be antisymmetric and will preserve the determinant of the Hamiltonian, okay? This will happen only at 2 points, or you know, only at the center of the Brillouin zone and at the edges. So you cannot find a matrix that will fulfill this for all values of k, but it's guaranteed that you will find a matrix that fulfills this for k equals 0 and plus minus pi over a. So it's not pi over 2, it's pi over a here, okay? The ends of the Brillouin zone. So I see I need to make some corrections here. This slide. Okay. So what is the thing here is, you know, the determinant of H. So how we know if the gap closes? So if the gap closes, if the energy E equals 0, is an eigenstate of the Hamiltonian, right? So it means if the determinant of H is equal to 0, the gap closes, because the determinant H equals 0 means E equals 0 is an eigenvalue, right? Remember this equation? Right? If E is equal to 0, it's an eigenvalue, so then the determinant of H is equal to 0. So I can know when my gap closes by just looking at the determinant of H. Okay. So the determinant of H, I can also write it like the determinant of this B matrix. Now this B matrix is skew symmetric or antisymmetric, so, and it means that they have a property. All these skew matrices, they have something that you can calculate with it, which is called the Pfaffian. And the Pfaffian is related to the determinant in that way. So the Pfaffian, so I'm not writing here the explicit calculation of this Pfaffian. It's a long formula with a lot of things. You can go to Wikipedia and read whatever it is. I just put into a couple of formulas here, one that is important for this case and one that you can use if you need to calculate it numerically. Okay, so what is the thing? The Pfaffian square will give you the determinant, so it means that the Pfaffian will, you know, can be equal to plus minus the square root of the determinant. So then you can see whether this Pfaffian is going to change the sign if you have a gap closing. Only if you have, so you can change the sign only through a closing of the gap, okay? So then you just can look at whether this Pfaffian is changing sign or not, okay? It could be plus 1 or minus 1, that's the sign. There is a small detail here, and is that actually the sign of this Pfaffian is not fully determined, in the sense if you change the basis, you may change the sign. But if you have the Pfaffian at k equals 0 and Pfaffian at k equals pi over a, you can show that if they change sign, they say sign simultaneously. So then instead of looking at or monitoring the changes of sign of one of them, you can just look at the product of them, okay? So if the product changes sign or not, Okay, this is essentially what you are looking. So this product will change sign only if the Hamiltonian close the gap at k equals 0 or k equal pi over a. Okay. So that's why instead, you can define this topological C2 quantum numbers typically refers actually like the topological charge because, it's 1 or minus 1. So this is winding number, just give you the number. This is typically called topological charge because it's 1 or minus 1, like E or minus E. It's 1 or minus 1. Okay. And it's equal this to the sign of the product of these Pfaffians of this B matrix that one actually have to find it, right? And then you can calculate it in that way. It's the product or the ratio is the same because the sign is the same. Okay. Now, in most of the cases, you will have actually to calculate the Pfaffian numerically. And so you can then use this formula here, this identity, to calculate it numerically. So for this, you will need the spectrum because you see all these things here are matrices. And then the exponential of a matrix is going to be, so you most probably will have to use this spectral decomposition so that you work with functions. Anyway, so how to build this matrix? Okay, so we can use the particle Hall symmetry, which in that case impose this property here. And then we know that my chiral, my charge conjugation operator can be written by this unitary transformation times the complex conjugation. So, and from this equation here, so, I just can substitute this C in here, and it follows, this follows, right? So the, the conjugation over H will make the transpose because H is Hermitian. So the complex conjugate of Hermitian matrix is just the transpose of this matrix. Right? So that's why I have here this transpose, and then you don't see K anymore. Okay? So you have this property, and you do a little of math here, so it is explained here more or less, step by step. You get all these identities. The important thing is that you get at the end this relation here. And now you see, you get this, if this is equal 1, then you are done. So you see that your B matrix can build in this way. Your Hamiltonian times this UC matrix that you know it because it's the matrix you have in your complex, in your charge conjugation operator, okay? So for this case, it happened that it works because actually for this symmetry, you have C squared equal 1. And if you calculate C squared, this is actually C squared. This UC you conjugate just will give you 1. And then you can show that then indeed this operator B is indeed antisymmetric. It fulfills this relation, okay? So now I know how to calculate B because my UC just tau x, right? So I have my chiral operator here was tau x k. So this UC unitary transformation in this specific case is just tau x. So I have my tau x. So this is my matrix, H tau x. And then you can calculate the Pfaffian by just calculating the determinant in that case at 0 and pi over a. So at 0 you will get this value, and pi over a you will get this value. So you can then look at the topological charge, the sign of the product, you will get the sign of this. And then you see this, this is going to be 1 or minus 1. If mu is larger than 2t is 1, so you get this trivial phase. If mu is smaller than 2t, then you get minus 1. Is in that specific case, is the topological superconducting case. All right? Yes?
Oh, you did like one is trivial and minus one is so much. Why you cannot switch the definition?
Oh, you know that this is going to be like that because if T is 0, so there is no hopping, so it's a trivial insulator. And So you can reach this in this case. In the other case, because mu and t are positive here, you cannot reach this other case. Because if t is equal to 0, it has to be trivial. So then you have only this possibility to be trivial, 1. Okay. All right? Okay, so, yeah, so then, from this model, I just calculated my topological invariant. So you could do the other way around also, okay? You can do the calculation of the Winding number. And this I will, you can do it at home, and you can do it by using this Hamiltonian, okay? So there is another way. So I told you before, I have this function before in the other case that depends on k. And from here I build the real part of q, which depends on k, and the imaginary part of q that depends on k, okay? And we have this matrix for, this matrix q was 0, q, conjugate, and 0. Okay. And then, so you can also write this matrix in this form, right? So you can put this q like the real part of q plus I, the imaginary part of q, and then write this q as some a sigma x, hx plus hy sigma y, okay? And hx and hy will be, essentially, so you can, this is real part plus I imaginary, this is real minus I imaginary, so it will be real times sigma x, okay? So this hx will be the real part of q, and this will be, so I have here, let's say, I minus I, so it will be whatever convention you use for this, plus or minus imaginary part of q. Okay? So then you see, this is just, you can build this vector h from this. So it's a vector, and this vector is going to be changing when you change q, when you change k. So this vector will just be moving and making this curve that I showed before, right? So before we have this, remember, and we have this circle. So this vector will be, when you change k, it just will be moving like that, okay? You can do this in this case also because, you can put this fake symmetry, and, you can write this, okay, I think you will have to, all right, so you will have to make the plot in this YZ because there is no sigma x here. You have sigma c and sigma y in this Hamiltonian. Okay? So to either rotate or you take your real axis, like, let's say, like the y direction, and the other ones, the real like the z direction, and the imaginary like the y direction. Okay? And you can do the same with it for this, but now using this Hamiltonian, and you should get what you will get. So you will get actually nu equals 0 and 1. So, which is the thing that will map these values. So you will get nu equals 0, exactly like this case, whether or nu equal 1. And then you will get for nu equals 0, because QC squared is minus 1 to nu. For nu equals 0, you will get trivial, so you will get QC equal 1. And from nu equal 1, you get minus 1, you get the topological one. So you see there is the same, you will get the same conclusions, okay? All right, so this was for this infinite system. So let's see what happens if I now make the cut and make a real chain. Okay? So I will skip this math of that. So you can go to this paper. You can go to the Wikipedia page. It's everywhere. This is, but I tell you what is the idea. But you can find it there step by step. So the idea is, remember what was the Hamiltonian I have. Let's go back. Okay, so I have this Hamiltonian, and all these C are the annihilation operator of particles, okay? Electrons. So the idea is I want to diagonalize this Hamiltonian somehow, okay? To see what is the spectrum. And for this, I will introduce a couple of new operators. These operators are these gamma operators here. So for each site, I will create a couple of these operators. These are the so-called Majorana operators. So then I will express the particle operators as a linear combination of these two Majorana operators. Okay? So I can, C is going to be then 1/2 gamma 1 plus I gamma 2, okay? And for each site, okay? At site I have this. For another site, I will have this with another I, okay? So I can combine these two equations, and I can also find the Majorana as a function of the particle operators, okay? And essentially, you will see, you see here that it's like also like a linear combination, equal superposition of particle and hole. Okay? Because this will give you like a hole, this creates a particle. So this Majorana is just like an equal superposition of an electron or a particle and hole. Okay. So what you can substitute these new operators, put it in your Hamiltonian, work a little bit things, and you will end up with this. This is the transform Hamiltonian. Okay. And this is for mu equals 0 actually. So the mu was put 0, I think, for this model. So you will say, well, what is the thing? There is nothing here, so I still get something in there. Well, there is something. The thing is, if you look carefully at this Hamiltonian, you see that there are two gammas missing in this Hamiltonian. So this, at the beginning I have all the C's, and since I have all these C's, I have all this gamma at each side. But after I do all this transformation, I end up with a Hamiltonian that is missing this gamma at position n and position 1. So the n gammas at the end position of this change are missing from my Hamiltonian. What does it mean if they are missing? It means that they have 0 energy. They don't have contribution to this Hamiltonian. The contribution is 0, okay? So it means that you have these states that are at the edge, localized at the ends, 1 and n side, with 0 energy. All right? So that is essentially the Majorana states. And you can see this if you plot the exact or the solutions of numerical solutions of this problem. And this look like that. So this is the numerical solution. Then you see here, this is actually in agreement with what we have here. So we saw that for, if mu is larger than 2t, then it's trivial, is smaller, is topological. And we see if mu is smaller than 2t, we are in this region here. It's topological, and we have these 0 energy states in the middle of the gap, right? When we go to the trivial, so the gap open, and we don't have these states anymore. So we have this trivial situation with the gap system, and here there is no gap because I have these states in the middle. Okay. Now you see there is a little bit disagreement between this and what we got, right? So because we got that for mu smaller than t, smaller than 2t, you should have this 0 energy state. But if you look close here to 2, there is not really 0, right? So it's have some finite energy there. And the reason for that is that this conclusion that we got, that this transition will happen exactly when mu is equal to 2t, is for this infinite chain, but this chain is finite. And so there is overlapping of these Majoranas, okay? So if you want to improve this, you will have just to make the chain longer. The longer you make the chain, the better it will agree with the conclusions we have. If you make the chain very short, by the way, you won't see any of these things because the Majoranas, they will hybridize and you won't see any zero energy state. They will get finite energy, okay? So you have to make the change long enough so that these two Majoranas at the ends don't talk to each other. If they talk to each other, they get energy, they get excited, so no zero energy anymore. Okay, any question?
And why we call this a P-wave?
Why we call it P wave? So you look at this, you know, remember this BDG Hamiltonian we have, it have this form. So electron sector, host sector, and then we have the deltas. And this was the superconducting gap. When I did all this BCS, I put this like a constant, right? Here, if you look at this, this is what is playing the role of these superconducting gaps. Actually, in this case, yeah, so you may, you know, the order of the basis will give you here this I sigma y or whatever. Anyway, what you have here is that delta is not a constant, it depends on k, depends on momentum, on the particle momentum. And it's odd in it. So this is a symmetry that it's a p-like symmetry, like this p orbitals that you have, okay? So that's why it's called a p-wave superconductor. It's a problem for realizing this because, as far as I know, we don't have any real demonstration that there is a p-wave superconductor in nature. There are some indications for some material, but it's not firm. So this superconducting gap is so small that you cannot really see, you know, proof that it is indeed what it's expected to be. So as of today, we don't know any p-wave superconductor in nature, so we have to engineer if we want to find this. Okay, but we have some clues already from this. It's a model, and it's a toy Hamiltonian toy model, but it will really tell you what are the ingredients you will need for this, for having or for engineering this topological superconducting state. And one of the things is we need to break spin degeneracy because this is what the model is stuck. Spinless, so I can separate the spins. So it means typically I will need, let's say, a magnetic field to break this spin degeneracy. What else I will need? Well, I need something that will link this spin to the momentum because you see, I don't have a delta that depends on momentum in my system. So you can actually gauge out this momentum dependence and put it on the other elements. So you will need something like a spin orbit coupling, which is the thing that will couple momentum to the spin. So all in all, so there are many proposed recipes to build this, but the main ingredients are this: superconductivity, because you need particle-Hall symmetry. You need Zeeman-like spin splitting, because you need to break the degeneracy between the spins. And I say Zeeman, but it could be also exchange interaction like we have before that split the spins, whatever thing that split the spin, okay? And this is just because it will break this gamma degeneracy, so it will break the spin degeneracy. And then if I tune my chemical potential or my Fermi energy in between, so I can ensure that only one of these spin will be prevalent. And then we need also the spin orbit coupling, which essentially gives me this, in a way, this K dependence of this delta. So here are some of these proposals. So this, let's say, quantum wire. So you can make a wire which is a semiconducting wire. So in a semiconductor that have spin orbit coupling, like this rational spin orbit coupling we talked before, now you put this semiconductor on the top of superconductor. And so because there is an effect of proximity, some of this superconductivity leak into the semiconductor. So this semiconducting wire acquires superconducting properties. Then you have in this semiconducting wire, you have superconductivity, you have a spin orbit, so you need, just to break the time reversal symmetry, you need to split the spin, so you need to apply a magnetic field. So you apply a magnetic field. So this is the magnetic field. This BSO is just this field, is the spin orbit field, okay? This one here. And then so you have all the ingredients in the system. You have to tune properly the system, and what is shown is actually if the Zeeman splitting energy is larger than the square root of the chemical potential plus delta square, you can enter in this topological phase. As you see here, we don't have a P-wave superconductor. This superconductor we have here is just conventional S-wave. Delta is constant, okay? But we have a spin orbit and so on, and they just happen to mimic this P-wave superconductivity in a way. Okay. So this was, I think, the first experiment, and you can also, you may not need actually magnetic fields. You can use magnetic textures, actually. A magnetic texture is something good because it actually gives the two things. They give you the spin splitting, and they give you also a sort of a spin orbit. So it makes the spins also do, if the texture is rotating, or it's half a helix, so the spin also will be rotating, so it plays a little bit the role of a spin orbit coupling. So then you can have, this is an experimental work actually, you can have in that case a carbon nanotube, and then you can have the spin texture here created by these arrays of magnetic layers. So you have the fringe fields of these magnetic layers make this spin texture. And the spin texture is equivalent to having Zeeman splitting plus spin orbit. So you can also, you can use just conventional semiconductor wire like here, and you may have a spiral phase on some of these ferromagnets or antiferromagnets and get spin texture from them. Or you can put some magnetic tunnel junction that you can control also this magnetic texture, or you can have Johnson junctions. So there are many different ways. So there are just a few of them. Quite biased, I think. I put most of my work here. But there are many, okay? So this is just for illustration. So you want to, if you make this model of, this Kitaev model for a wire now, not with a speed wave of Kitaev, but just considering a Hamiltonian, this is a 1D Hamiltonian, okay, with conventional superconductivity delta constant. We have a spin splitting, so this is the Zeeman interaction B with sigma. B is along the magnetic field along the x-axis, and we have ratio spin orbit coupling. Okay? With this simple Hamiltonian, you calculate for a wire, so you have to have your boundary conditions for the wire. This is what you will get. So this is the spectrum here. And as you tune the Zeeman splitting, this BC is the Zeeman splitting, so you can tune the system from trivial, when you have this gap, into this topological phase in which you start to see the Majorana states right in the middle, okay, at zero energy. Now this is for a very long wire, it's 7 micrometers. If you make the wire small, then these Majoranas at the end start to talk to each other, and the energy goes away from zero, okay. So you start to see this wiggling here, this oscillation of the Majoranas, because, well, they are hybridizing with each other. If you look at the probability density, so to see where these Majoranas are, so for this, for these 7 micrometers, you get this blue and red. So you get one Majorana here. So this is the direction of the wire. So at one end of the wire, you get this very high probability for one Majorana, and at the other end, you get the other Majorana. And here, so they, in the middle, you see they're still talking a little bit. If you go away from, from this region here, and you are somewhere here, then you may get all this wiggling because they are talking to each other. Energy goes to finite energy. All right? Any question? Some questions? All right, so what is the idea of this, to use the Majorana? So if you use this two-level system for doing a quantum, building a qubit, typically you will have the, each qubit in some position. So, and the information of this qubit is just local. So you have the qubit here. I don't know. Let's say I'm using the 2 levels of one atom for doing that. Okay? My atom is here, my 2 levels are here, and any perturbation that I have around this atom can change the levels. Okay, the energy difference between these levels, it can affect my qubit. If I have the qubit in a superposition, these 2 levels, this qubit can decohere because of interaction with anything that is around this atom. So it destroys the information, and then you have errors in your calculation. So it means that you will need to make error correction, which is not very trivial for quantum systems, because unlike classical systems, you cannot make copies of superposition states. So in classical systems, it's easy to make error correction. You just make 100 copies, and if 10 copies get corrupt, I still have my 90 copies. Okay, but in quantum system is tricky because you cannot do copies of superposition state. So you can prove this mathematically. It's called non-cloning theorem, so you cannot make this copy. So making error correction is tricky, and typically involves the use of many, many other qubits just to make error correction. So it's a big problem, error correction. You can do it, but it's very expensive. And it's actually the bottleneck of quantum computing. So the idea of using the Majoranas is, well, these Majoranas will store the information non-locally. So you can have these 2 Majoranas at the end of the wire. This Majorana must come in pair because it's imposed by this particle-Hall symmetry. Particle-Hall symmetry tells you that they have to come in pair. You can have 1, you can have 2, 4, 6, but not 1, not 3. Okay, they have to come in pair. So now you have these 2 systems, and you store you build your qubit with these 2 Majoranas. Now the Majorana that is at one end, you may have some perturbation, but this perturbation cannot destroy the information of this Majorana, because for destroying this Majorana, it will also have to destroy the other one because they have to come in pairs. So you cannot just destroy one without destroying the other. But the other is far away, so this perturbation is not reaching the other in any way, right? So the information is now non-local. So whatever I have local cannot destroy this information. So it is protected now against these local perturbations. So that is the idea of using the Majoranas. According to the Majorana 2, the Microsoft recently report, so they can reach coherence time of 2 seconds if this is true. Okay, it's not review this paper, and so I don't know if it's true or not. I mean, it's true that they reported, but I don't know if it's correct or not. Okay, so a question.
The Majorana state is energy level is at
Zero energy.
Then how do you separate like the 2 level system?
This is this slide. You have to build the qubit in a different way. So you cannot go through this 0 and, because you don't have 2 levels, they are degenerate. Okay? So this is the way you build the qubit now. So the qubit is now, if these Majoranas are empty, you will call, let's say, 0 state. If they are occupied, you call the 1 state. So you fuse them, meaning you bring these Majoranas together. When they fuse, they get finite energy. So they form a quasi-particle excitation. So you will get an extra particle, extra charge, if they are occupied. If they are empty, you don't get this extra charge. So the way you will read the information. So typically, you will have to create the Majoranas, occupy them or empty them, then do all the computation, and then you will fuse them to read the state of the qubit. Okay. So what is the nice thing of these Majoranas is, again, that since they are degenerate, so typically you have, that you have a wave function of many identical particles, you exchange 2 particles, and the wave function change by a phase. So this phase could be 0 pi, 0 for bosons, pi for fermions. In 2D, it happened actually that it could be any other value, so we call it anyons. But here, so since the states are degenerate, so the solution is not just one state, it's a linear combination of these two states, right? So any linear combination of these two states is a good solution. Now, when you exchange them, you go back to another linear combination. So it's unwarranted that you will go to the first linear combination. All of them are good, equally good. So you, in general, go back to a different linear combination. And we know from going from a linear combination to another linear combination, what I'm doing is just applying a matrix. So a matrix is the thing that would change a vector, a linear combination of vector into another linear combination of vector. So essentially, when I am exchanging this particle, I'm just acting on my wave function with a unitary transformation. So I'm doing quantum gates just by exchanging these particles. So the quantum gates is the thing that you need to build your operation, your computation. Okay, so the idea is then that you properly, braid these Majoranas to build your gates, your unitary transformation. The idea of the computation then, this is the scheme of a quantum computer, a topological quantum computer. So you have the vacuum, so it means just your superconductor, no Majoranas, anything. You create your Majoranas, and then you initialize. Initialize means, I need to put this QE in the 0 state, well, I will leave it empty. This one, I want to put it in the 1 state, I will occupy it, okay? They are still, all of them are apart from each other. Then I start to exchange them while they are apart from each other. By making the exchange, I'm doing the operations, I'm doing the gates. So this is the implementation of the algorithm, all this braiding. At the end, I need to read what is the state of the qubit, so I will fuse them and measure whether there is a charge, extra charge for each of them or not. So I can figure out what is the state of the qubit. And this will give the computation. So the way you braid them will implement different quantum gates. Here, for example, if I have 4 Majoranas, so I have 2 couple of Majoranas. If I set 1 Majorana of one pair and 1 Majorana of the other pair, and I exchange them twice, I will be doing a NOT gate. So meaning if let's say my 4 Majoranas are empty at the beginning, when I do this double exchange of 1 Majorana of each pair, I would end up with occupied Majoranas. So before they were empty, after I do this, I end up with the being occupied. So I fuse and I get 2 particles, 2 charges extra by doing this. I go from 0, empty, to occupied 1, so it's a NOT gate. I will show you more or less how to do this in principle very quickly. So let's say that you have a 2-dimensional electron gas. You put the superconductor, so you have now superconductivity in this 2-dimensional electron gas. Now you put a magnetic texture. You can create this texture with some magnetic nano junction that you put on the top, these magnetic junctions here. You can change the texture. So if the junctions are in this anti-parallel configuration, the fringe fields are going to be very small. But if the junctions are in the parallel configuration, meaning these 2 magnetic layers are parallel, then you have large fringe fields. So you can make an array here, for instance, array the 3 by 3 of these magnetic junctions, and you can create this texture to go in some direction. In this case, the texture is going through in this direction, and here is almost 0. You get this effective wires in there. So we don't have physical wires here, but we have this effective wire, and then we have these 2 Majoranas at the end. Then I can switch other junctions so that I can change the texture to make a different wire, like this, and then this will move this Majorana here to here. So then I can start to all this switching so that I can change everything. I can rotate, move these Majoranas around. And eventually, I can do like this, let's say that I have my nanopillars are on in these 2 positions, so I have just essentially like a small quantum dot created by this texture. And I will create them empty. So it is empty, I have these 2 dots. I don't have Majoranas because they are just fused. They are just like quasi-particle, but they are empty. So what I do now, you start to switch the other nanopillars, so this wire start to extend. And let's say you start to increase this one, so this wire go like that, then the other wire go like that, then you go back, and then you fuse them. And you should get, you start here with empty states, you end up with occupied states. So if you look at the reference frame of this, you have these 4 Majoranas, gamma 1, gamma 2, gamma 3, gamma 4. If you look, if you are in this gamma 2 reference frame, what you will see when you're doing this operation is like gamma 4 going around gamma 2, okay? So you can see here more or less how this gamma 4 is going around gamma 2, okay? So it's essentially like one going around the other. This is a NOT gate, so I just doing this operation, I start from 0 state, I go back to the 1 state. All right, so then I just fuse them, I measure my extra charge. You can also do a control experiment by changing the order of operation so that you don't really exchange. Here you need to do exchange with the Majorana from different pairs, but if you do exchange of Majoranas within the same pairs, this is trivial. So you can change the order of operations, and then you will see that the result is different. So it actually shows that it is non-commutative in the sense that it depends on the order of the operations. All right, so this is the simulation here of this, what I showed you before. We start here with these empty dots, and we make this wire, switch on this junction, so we make the wire. We start to get Majoranas at here and here. So the red ones are actually the charge density, because Majoranas are chargeless, because it's equal superposition of particle and hole, so they have no charge. That's how you see this is very small. This is the scale here is 10 to the, yeah, it's very small scale, so I don't remember now. Anyway, so this is the probability density, Majoranas here, but the density, the charge density is almost 0 because they are empty. Okay. Now you create this wire, you move this, then you create another wire. So from here you go down, and then after that you fuse them again. So these 3 go here and 4 go back up, and then you end up with this probability density still here, but then you have this extra charge, and this, you compare the scale. So here you really have charge. So essentially, you start with these 2 couple of Majoranas. They are empty. You do this operation, they start to be occupied. You fuse them, and you get these 2 extra charge. And you will tell me from where I get this extra charge. From where? From the condensate. So you're just pumping a Cooper pair from the condensate into the Majorana state, and when you fuse them, you get these 2 extra charge. Okay. All right, so with this I will conclude. And so you have any questions? Yes. All right, so I hope you have learned something in this course. I will upload it. I give the.
So I'll upload the lectures on the page. So Alex is still here. He's sitting in the queue for the office. If you really want to discuss, show your results.
Absolutely.
I think it's a great opportunity just to.
Yeah, it's very good for me. Yeah, I just want to learn some way I just introduce myself. I did not introduce in this topic before. Now I realize.
Right, so this course is not for making an expert, it's for giving you courage to read other things, okay?
Okay.
So,
Yes.
so Majorana state means it's a state that can be occupied by.
Like any state, could be occupied, it could be empty. Right.
It's a special state.
Okay, so I maybe I skipped this figure here, but maybe. Okay. So here is more or less the picture. So let's say you have your initially you have your Majorana, you fuse your Majorana, so there are no Majoranas, so they are fused, and they have some finite energy. So it's like you are here at the top. So you have a couple of Majorana, but they are fused. They are here at at the top of the mountain, some energy, okay. And your buckets are empty, so there is no Majoranas in there. Okay. There is no, so there is Majorana state, but they are empty. They are not occupied. Now, when you start to make this, you have a dot, okay? And when you elongate this dot, so these Majorana start to get apart and apart, and the farther away they get from each other, the closer to zero energy they get, okay? So you go down to the river. So the river, let's say that this is zero energy, okay? This river is full of Cooper pairs. Right? It's the condensate, it's the energy of the condensate. But when you are there, because you also have zero energy, it doesn't cost any energy to fill your buckets, okay? Your state can get filled from the Cooper pairs, or they can be empty if you don't want to fill them. So if your operation don't allow to fill them. So essentially you have 50-50% probability that they will be empty or not, okay? But then what you do is this braiding to increase the probability to get it occupied. So you do this with the two, with these two pair of Majoranas. Now comes the magic, which I cannot, translate in here, but the magic is that you do this braiding between the Majoranas from different pairs. And this made the magic, so it actually increased this 50-50 probability into 100 probability that it will get occupied, so that it guarantees that you will fill your buckets. Okay, now your Majoranas are empty, but still at zero energy. So you cannot distinguish them. Then now you bring them together. So you go to finite energy. When you bring it together, so they fuse, and they just form a particle. If they are occupied, if they were occupied, you will get 2 extra charge. And here you get, a charge, and here another charge. So 2 Majoranas fuse, you give a charge. The other 2 fuse, you give the other charge, so you get 2 charges. So essentially, what you did is, well, you went to the river and you filled your bucket. So you're pumping these Majoranas at this Cooper pair that you got from the river, and bring it into excitations. Okay?
The Cooper pair is also like a pair, right? So does that mean like 2 Majoranas is occupied by the same Cooper? They can form the same Cooper?
This is not, so this is the magic is that there are no Cooper pairs anymore, okay? So when they fill the Majorana, so they are Majoranas, they are not Cooper pairs, okay?
Like Cooper pair.
So it's like it doesn't cost, it costs energy to, if you want to directly destroy the Cooper pair, okay? It costs energy, you have to apply this delta. But since the Majorana have the same, when they go to zero energy, they have the same energy that they condensate. It does not cost any energy to convert this Cooper pair into a 4 Majorana, into 4 occupied Majoranas. Anyway, if you want to measure this charge, you still have to gain energy, so you have to bring it back to finite energy, so to fuse them. And then you can measure them, because if they stay at zero energy, you cannot really measure the occupancy of them. Okay. All right?
We are closing.
Okay.
Thank you, Alex. And tomorrow I will upload the Moodle final date, the corrected with David's editing, and also Alex.
Yeah, so I will need to make this correction.
Thank you very much.